Hello, everybody. My name is Mohit Garg, and this is joint work with Sunil Saraswat. And I'm going to point on this board, so if you guys cannot see, you feel free to move here or just guess where my pointer is. So I am hoping this talk is going to be a very simple talk, and I'm going to tell you about a problem which is centuries old. It's the exchange problem. So let me motivate the setup, the problem statement by, sorry, the camera, I should be here. Okay, so imagine you run a coin shop and you deal in this American silver eagle coins. Okay, this is a $1 coin, but due to the quantity and quality of silver used in it, it is worth much more. And I would like you to guess what the price of this coin will be. Uh, and here is a hint. So throughout the day, buyers and sellers get in touch with you and they tell you how many units they are willing to buy or how many units they are willing to sell and what price they are offering for it. So you get the list of bids from the buyers and a list of asks from the sellers. So let's understand what these bids and asks are. So this is bid one. So this buyer offers to buy 3 units, up to 3 units of this coin, and he's willing to pay $93 for each unit. And so on. There are these 7 buyers, 7 bids, and 6 asks. So this seller offers to sell 8 coins, and he says, I want at least $95 for each coin that I sell. Okay, so you get this list of bids and asks, and you wait till the day ends. You then try to match the buyers and sellers. So what would be a feasible solution? If you run the shop, a feasible solution will look something like this. So these were the original lists. You say buyer, so you will create transactions. So matching is a list of transactions. So bid one, ask for. So buyer one, you go and buy 3 units from seller 4 and pay $92 for each coin you buy. And similarly, so here is, so this is a feasible solution, and all the natural constraints should be satisfied. That is, this $92 should satisfy buyer one's limit price and seller four's limit price. Okay, and if, for example, let's look at, here is a transaction between buyer 4 and ask 6 for 7 units. So ask 6 wanted at most 9 units to be sold. So and there is no more ask 6. So you are only matching him up to sell 7 coins. So that is fine. You should not match him up to sell 11 coins because he has only 9 coins to sell. So these are the natural constraints. Limit prices should be respected. The quantities should be respected. And such a list is called a feasible solution. It's called a matching. And what is the volume of this matching? You just add the quantities up, 22 coins. So such a matching, you are saying that 22 coins will change hands from the sellers to the buyers. Okay, any questions so far? Yes. You are asking about the volume? Volume is the, so total transaction. So seller 4 will give 3 coins to buyer 1. Seller 1 will give 5 coins to buyer 2. So the sum of these coins, the total coins that will go from the sellers to the buyers, is called the volume of this matching. Price. No, that is just definitional. There is no deep reason for it. We'll see. I mean, yeah. So the two problems that we consider is, so maximum matching. So what is the objective? You have to produce a matching, but what are the objectives that you need to have? So there are two popular objectives. One is to determine a maximum volume matching, okay? And the second objective is determine a maximum volume matching subject to the additional constraint that all transaction prices have to be identical, okay? So one is unconstrained maximum volume matching, where different transactions can have different transaction prices. And one is a maximum volume matching, where every transaction should have the same transaction price. And this problem gets solved every day around the world at stock exchanges to figure out the opening prices and closing prices of stocks. And maybe this problem gets solved in buying houses and stuff like that. But maybe other places also, which I'm not aware of. But both of these are the two popular problems around it. And that's why this should answer your question, why volume is important, because it is getting used in the real world. So maximum volume matching and maximum volume matching subject to identical prices. It turns out both these problems have very simple algorithms, and their running times are n log n. They're pretty fast, and for both the objectives, you have almost identical algorithms. These algorithms start by sorting the list of bids and asks by their prices, and then there's a top-down greedy matching approach. So let me just read it very quickly, but then if you don't follow, don't worry, I will show it in an example later. So first you sort the list of bids by decreasing prices. And for maximum matching, you sort A by the list of asks by decreasing prices. But for uniform matching, you sort asks by increasing prices. Okay, and this is the only difference. For two different objectives, the sorting order of the asks just changes. After that, it's the same algorithm. You take the top bid in the sorted order and the top ask A, and you ask, are they tradable or untradable? Tradable means, are their prices compatible or not? Buyer should pay at least the price the seller is asking for. That is the meaning of being tradable. So if this top bid and top ask are untradable, you just delete the ask from your list. But if they are tradable, you match them as much as possible. That is the minimum of the quantities that they have offered to sell. And then you decrease the match units from B and A, and you recursively solve the problem. So let's see this algorithm. So maximum matching algorithm. So see, I have sorted the bids in decreasing prices. So this is a 98 rupees this buyer is willing to offer, and then the prices are going down. And this is the least competitive seller. He's charging $99 per coin, and then to the most competitive. So first step, you sort them. It takes n log n time, and then linear time, you will produce the matching. You take the top bid, and you take the top ask, and you check, are they tradable or not? Are they tradable? So this is $98, and the seller is asking $99. They're not tradable. So you just delete A3 from the list. Okay. Then you check the top bid again, which is again the same one, and here top ask. Now they are tradable. Their prices, in fact, are identical. So you create a transaction between them, and the transaction you can create is of quantity 6, because this guy is selling only 6 units. So you get the first transaction between B5, A5, 6 unit, and the price is 98. Then, you now remove this, and you decrease this quantity to 1, because 6 units have come out here. Then you ask, is B5 and A2 tradable? Again, they have the same price. They are tradable. You create a transaction, and this now goes away. This quantity reduces to 3. Then you take the next guy. 97 and 98, they are not tradable. The buyer is paying 97, seller is asking 98. Then you delete this, and this way you continue. I hope this is clear. Just a top-down greedy approach. And whenever things are not tradable, you delete the ask and move down, and repeat the same thing again. So this is a linear time algorithm, and here you get, so after the sorting step, you just took linear time, linear in the number of bids and asks. And so here it turns out that the volume of this matching is 29. And it's interesting to think why this is the maximum volume matching possible. I'll let you think offline. Moving on, let's do the uniform matching. It is slightly simpler, but it's the same algorithm. Now the bits again are sorted the same way. The asks are sorted in the reverse order. You see the most competitive ask is now on top, asking you $91, then 92, and so on. And again, you do the same thing. You check, are these two guys tradable? Yes, they are tradable. You match them as much as possible. You reduce the quantities. So 7 goes, and here only 2 remains. Then B4 and this again are tradable. You trade them and you keep doing this, you will get this table. I have not, notice I have not put the prices as yet. So after a while, you will find that B7 and A1, they are tradable, and B7 has some leftover quantity, and B7 and A2 are not tradable, because at this point you just delete it, and then you have to delete everybody because it was sorted in this order. So at this point, your algorithm terminates. And now what is a good price you can put? You see, so these guys, these 3 top guys got matched with these 3 top guys, and their prices are sorted in this way: 91, 92, 95, 97, 97, 98. So any price between 95 and 97 is acceptable to all of them. So we will just put a price of 95. There's no rule which one to pick. You could have picked 96 or 97 as well. Let me just put 95. Okay. I think this clicker has stopped working. Yeah, okay. So I will, now I can just continue my talk from here. So observe, so 95 is the price you put, and the volume you get is 22, which is lower than 29. But the thing is, all transaction prices are identical. They are 95. One more thing, observe that I could have created other things. All these matched buyers and matched sellers, they need not have been matched in this order. Any permutation of the buyers and sellers could have been matched to each other, because all are happy with the price 95. Right? So keep that in mind. And the things that don't get matched, actually no 2 of them are tradable. The things that have crossed out, they are not tradable at all. Okay, so this is the 2 algorithms. I will again, it's a very simple argument why this is the maximum possible uniform price matching. Let me tell you in one sentence, although I won't have the time to tell you, show you exactly. So I told you any price between 95 to 97 was acceptable. So first proof that that is true. That is, if you had a price of 94 or lower, actually this will not work. You won't get volume 22. Right? Because the number of sellers willing to sell at that price is strictly less than 22. Okay. And similarly, the price could not have been 98 to higher, because the demand would have been lower than 22. And that is, and then you can prove that the correct price has to be between 95 to 97. And then this is the only possible, up to permutation, this is the only possible matching with volume 22. So that is a proof of correctness. So in this work, we are these algorithms time optimal? And we prove that for maximum matching, n log n is the best you can do in the comparison model. There's no algorithm that can get rid of the sorting step or any n log n time. So n log n time is required for maximum matching. Let me give you a quick argument for that. Let x1 through xn be a random permutation of 1 through n. Okay, you create a list of bids and asks where the bid prices are all have quantity 1. All have quantity 1, both the bids and asks. And the bid prices are x1, x2 up to xn, and the ask prices are 1, 2 up to n. Now, what is the maximum matching possible here? We don't, x1 to xn is a uniformly random permutation of 1 through n. The maximum matching is of volume exactly n, where price I buyer is paired with price I seller. price one buyer with price one seller, and that's a unique matching. So now if you run any maximum matching algorithm, let's say it produces some transaction, now you can recover the X1, X2, and so on. X1 was buyer one's price, but it gets matched with seller 4, which had a price 4 and transaction price is 4. So X1 has to be 4, and X2 has to be 5, X3 has to be 2, and so on, right? So the maximum matching algorithm actually helps you figure out this uniformly random permutation. So let's say the algorithm makes T comparisons. Per comparison, it is getting only one bit of information, whether this is smaller or that is smaller. But it figures out log of n factorial bits of information. So T has to be at least n log n, because log of n factorial is n log n, roughly n log n. So T has to be at least n log n. So that is this proof is very informal, but it can be formalized with entropy. If you want, in the paper we do a much more stronger proof, which also proves a better lower bound in a stronger model, binary query model, where we prove only n square root log n lower bound. If you want to work on a challenging and interesting open problem, can you improve this lower bound in the binary query model? I won't explain right now what the model is. But yeah, that is a good open problem, still open from centuries. Now, we tried to do the same thing for uniform matching, but we ended up giving a linear time algorithm for it. So uniform price matching actually can be done in linear time. And in one slide, I will tell you what is the algorithm hiding the details. So what you do, we want to get rid of the sorting step, essentially, because sorting step takes n log n. So what you do, you take the bit, we cannot sort the list of bits, you find the median element, which can be done in linear time, right? And then you apply partition based on this price P. You apply partition based on this price P. So things above will have prices strictly more, and things below will have prices strictly less. Let's say quantity of all these guys up to here is Q prime, then you do a weighted selection on the right hand side, find the element so that its quantity till here is Q prime. Let's say that element is P star, then again apply partition here so that the most competitive asks are above here. So things above need not be sorted and things below need not be sorted, but they are smaller, they are greater than P star above and smaller than P star below. And then you ask, is this median bit and the corresponding ask, are they tradable or not? If they are not tradable, imagine what would have happened in the original algorithm, the one I showed you above. The algorithm would have stopped before coming to this step because these guys are not tradable. So you can safely discard the things below, right? And recursively solve the problem only on the top half. Okay. But if they are tradable, then what would have happened in the original algorithm? Sorry. If they are tradable, in the original algorithm, they would have come all the way till this point and every matching would have happened because things in the original algorithm that remains untraded, they were not tradable. So in the original algorithm, with the sorting, it would have matched all this way and gone below. So in that case, you also match things on top. And as I told you, things on top, they all agree to a common price. So their ordering doesn't matter. Just match them up. And then you so you match them up in linear time and then recursively solve the problem on the bottom half. So so running time. So we using linear time, we halve the problem size. So this is linear. And that's the end of my talk. I will conclude by saying, making a few comments. Firstly, why did we look at this question? We were not working in this space. We were trying to develop a formal framework for exchange design and regulation. Essentially, if you ask what New York Stock Exchange does, nobody really knows. If you just go by their technical details, they will give you examples of how they match things, etc. So the kind of work we did is for model exchanges, we had declarative specifications for that what they are supposed to do, and then we made a product showing that if you give us their order book and trade book, we can tell if the rules were followed or there were violations. And this was done with formal methods with computer checked mathematical proofs. So our guarantees are the best guarantees that there are. And there we encountered this problem. This problem is solved in exchanges around the world, but nobody knew it can be done in linear time. Although our work is not practically relevant because n log n is fast enough and sorting algorithms are very fast, but still it's good to know that theoretically it can be done in linear time. For maximum matching, you cannot do it in n log n time. And actually, in our paper, we handle a slightly more general problem where there is a notion of fairness. Not just you want to find a maximum volume subject to uniform price, but maximum fair matching subject to uniform price. That also can be solved by the same ideas. And finally, I would like to thank the organizers, and especially Professor Christine, for partially supporting my travel, without which I would not have able to make it here. And thank you very much.
Okay. Yes, there is a question. No. Oh, Guillermo. Let's follow.
We can't be Byzantine around here. Great talk, by the way. Two quick things. Number one is, I guess, the argument you have, which is very nice. I like the idea of essentially recovering the sorted indices from the matching is very nice. It gives you for both deterministic and randomized protocols the lower bound.
Yes.
Right. So any protocol succeeds with any probability,
yes.
in fact, even for arbitrary computational models.
Yes.
I'm a little confused about the binary model. I don't know if you can describe it in
binary
sentences.
So binary query. So in comparison model, you can take two numbers, a price and maybe another number or two prices, and an oracle will tell you which one is greater.
Yeah. And essentially you get only one bit of information.
So in a binary query model, you can again take two of these prices or a number and a price and give it an arbitrary Boolean function. And it will say whether it is true or false. And each time you make an oracle query, instead of just comparison, each time you can ask whether the square of this is a prime or not, modulo the second number. You can ask any query, any true-false query with any arbitrary function. So that is a binary query model. So comparison is just one Boolean operator on two numbers, right?
Sure.
But you could think of an arbitrary Boolean function from reals cross reals, naturals cross naturals to 0, 1, and you can apply that function. And each time you can apply a different function.
Why is that not n log n?
We don't have a proof.
No, but the proof
because
the proof in Fanon's inequality tells you, look, you're choosing between two possibilities in your sample space for your like Markov or channel or whatever, right? So I think you immediately implies n log n actually for this model too. In fact, any binary query should give you n log n.
Yeah, it's sort of, so is it? Yeah, I need to think a little. Maybe you are right.
I think we should write it down, but I'm pretty sure any binary query where you only get 0, 1, the maximal, like your mutual information is lower bounded by or upper bounded by the entropy of that variable, which is less than log 2. So it should be the same. But anyways, cool. Very awesome stuff. This is like, I love the like very simple.
Yeah,
very
but
clean.
I'm only worried about if the functions are changing, if that makes a difference or not. So maybe that has information that can go in. So maybe we'll discuss this a little bit after the talk. There's a subtlety. So
yeah, that's good. Yeah. Thank you.
Thanks.
Okay, and another question. Can you pass the mic?
I have like two questions, I guess. What are the exchanges using currently? Is it like maximum matching or uniform matching or kind of a hybrid? Or
uniform matching usually, at least exchanges in Europe. And I think NASDAQ also does this. So this is 10 minutes at the beginning of the trading day. They collect all the orders and then they do this. uniform price maximum matching they solve. And that is the price you see. Apple opened at this $2,000. So that is, they're doing this algorithm, uniform price matching. Not ours, but the
And then
other one.
in that sense, is uniform matching, do they match it as the upper bound price or like the lower bound price? Because like there's this
So usually the bid-ask spread is much lower. In my example, it was very high. I don't know if they round it off to some 5 cents, and there are rules for this. They take the midpoint. If the previous day's close was something, they do something. So every exchange has their own rules for this. Like in that gap, which price to pick up.
Okay.
Usually that is specified. Like
And one thing I still haven't really understood was why are they trying to maximize the number of assets transferred and
yes, so
not
let's
the
say you take a commission per transaction. Every client comes to you, you charge a fixed price, then you would like to maximize the total number of units being exchanged. So stock markets are, in many countries, they per unit they will have a fee, which will be like 1 cent or something,
okay.
or few cents. I don't know the exact amount, but yeah. So then it makes sense to maximize the volume. Just that the regulators are not happy with maximum matching. Otherwise, all stock exchanges will do maximum matching instead of uniform price maximum matching. And why uniform price? Because since you are trading in the same product, you like every buyer and seller to pay the same price. So that is why uniform matching makes it's more fairer than maximum matching.
Okay. Yeah. Is anyone using maximum matching?
Yeah, so maybe one has to look around. Like I'm sure in the real world it gets used all the time in property, in retail markets here and there, but I don't know if in a organized exchange it is getting used or not.
Okay.
Yeah.
Thank you for the talk.
All right, so let's thank all the speakers of the session again.